तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We started mentioning, yeah? I started mentioning what the adjoint of an operator was. We still have a little bit of mathematical preliminaries to do, but then we need to also get started with the quantum mechanics. So let me do this in juxtaposition. As and when I need a little more information about operators, I will take a little break and talk about this like a lemma or something like that, and then we come back to the main physical point. Okay. So one of the things we do need, however, is the idea of a vector space, a linear vector space, which is infinite dimensional, and I mentioned that two notable examples of infinite dimensional vector spaces, one of which was L2 and the other was L2 in some specified interval. So we talked about the space of square summable sequences, and we talked about the space of square integrable functions defined for some real variable x running between a and b. Okay. Now these two spaces have a special role to play in quantum mechanics, because you will see as we go along that the states of a system would be described by vectors in a linear vector space, and the linear vector space would generally belong to one of these two spaces. So this is the physical reason why we are actually interested in these two spaces in particular. Now when we talk about infinite dimensional spaces, there is also the question of convergence. I did not pay much attention to it, so let me specify, spend a few minutes and talk a little bit about the convergence of states in vector spaces. Before that, notice that if I give you a complex number z, a sequence of complex numbers zn, z1, z2, z3 etc. formed according to some rule, the natural question that arises is, does this sequence converge to a limit or not? As n tends to infinity, does it converge to a limit or not? If it does, then that would be the limit point of this sequence, and then one could ask what kind of sequences would converge, and these are called Cauchy sequences, and a Cauchy sequence implies that the modulus of Zn minus Zm tends to 0 as n m tends to infinity. In other words, if the sequence is such that the difference between Zn and Zm modulus, this modulus goes to 0 as both n and m tend to infinity, then I call it a Cauchy sequence. Such sequences converge to limits, definite limit points. This immediately implies that limit n tends to infinity Zn exists. It implies that this sequence has a limit point which is some complex number. This limit point exists. This concept is carried over to state vectors. This is the concept that we need, the idea of a Cauchy sequence. Now not all sequences are Cauchy sequences, you can easily construct sequences. For example, if Zn is minus 1 to the power n, then of course even ones are plus 1, odd ones are minus 1, and this sequence does not converge to any limit at all. On the other hand, if this is true, then this suffices to show that the limit of this sequence exists. Okay. Now as you know, a set of points which includes all its limit points is called a closed set. So if you take the sequence Zn and you include the limit as n tends to infinity Zn, you include that limit point, then that set is a closed set or a closed sequence. Now taking this over to the idea of vectors in a linear vector space, this sequence in a linear vector space psi n is a Cauchy sequence if limit of the norm of psi n minus psi m 0 as n m tends to infinity. So this vector difference psi n vector minus psi m vector, that vector must have 0 length in the limit as n m tends to must tend to the null vector as n and m tend to infinity. Then that sequence is called a Cauchy sequence. Okay. Now a linear vector space has a large number of vectors and there is no guarantee that every Cauchy sequence has a limit point which exists in the same space, no guarantee at all, right. If it does, if every Cauchy sequence, we are guaranteed that Cauchy sequences tend to limit points. This means, by the way, this implies that the limit as n tends to infinity psi n equal to some psi, this limit, this is the limiting vector. So every Cauchy sequence converges to some vector, but there is no guarantee that that vector is in the linear space. Okay. If it is, then this space is called a complete linear vector space. So if of every Cauchy sequence in a linear vector space is also in the linear vector space, then V is complete So we will see why we need these ideas. For finite spaces this does not matter at all, it will turn out that every finite dimensional vector space is in fact a complete vector space, because you form all sorts of linear combinations, you add them up and so on, nothing will happen, it will never go out of this space. On the other hand, in the case of infinite dimensional spaces, you have to specifically make this requirement that the limit point of every Cauchy sequence remain in the space, in the linear vector space, because we are going to have operations with infinite dimensional spaces, we need this. If this is so, then the linear vector space is said to be a complete linear vector space. And in quantum mechanics we are going to use all the time complete linear vector spaces. In fact, we also need the idea of an inner product, we have already talked about the scalar product. So a complete linear vector space equipped with an inner product is the space that we use in quantum mechanics, and it is called a Hilbert space. And in quantum mechanics we are going to use Hilbert spaces. It will turn out that these are the natural spaces in which the states of systems, state vectors of systems exist. The reason you need, again I repeat, you need these mathematical niceties, none of which I am proving. The reason you need this is to make sure that operations with infinite sequences, infinite dimensional spaces and so on do not lead to errors. It is simply to make sure that everything is completely rigorous. Now all finite dimensional linear vector spaces are complete, and once you define an inner product on them, they actually are Hilbert spaces. Okay. but it is only the non-trivial cases are the infinite dimensional spaces. Now even given a Hilbert space, we should now ask what about basis vectors in such a space, and of course as you have seen, a basis set in a linear vector space is a set of linearly independent vectors which span the linear vector space, no directions are left out completely, and then once you are given a basis you can make it orthonormal and so on. Now there is no guarantee that given an arbitrary linear vector space, infinite dimensional space, there is no guarantee that you can find a basis set which is actually denumerable, namely that you can count off vector 1, direction 2, direction 3 all the way to infinity, no guarantee at all. If you can, then it is a countable or denumerable basis. So one more little piece of technicality is needed. A Hilbert space, we are going to work only with Hilbert spaces with a denumerable basis, let us call them phi n equal to 1, 2, 3 ad infinitum, in general ad infinitum. If it is finite dimensional it ends up at some point. A Hilbert space with a denumerable basis is called a separable. We are going to work specifically with separable Hilbert spaces. There are technical cases where you do not have a separable space, and then this is outside our purview of our course here. Okay. Now once you are given the fact that you are going to look at a separable Hilbert space of this kind, then it means that any vector psi in this space can be written down uniquely in an orthonormal basis. If the basis is orthonormal, can be written down in the form n equal to 1 to infinity some Cn by n. Okay. So the Cn's are unique quantities. Given psi you can find Cn uniquely, and of course the inversion formula Cn is just phi n psi, because this is an orthonormal basis. I will assume always that whatever basis you give me it is denumerable, and I will make it orthonormal by the Gram-Schmidt procedure. Then this is the expansion and this is the inversion formula. So the set of numbers Cn suffices actually to specify this vector uniquely, and moreover look at the fact that we want these vectors to have finite norm. We are always looking at vectors of finite norm, which means psi is nothing but n equal to 1 to infinity mod Cn squared. This quantity here is the norm of the vectors. So by definition this is the square of the norm, and if this is finite it means this is finite. And what do you call sequences in which this quantity is finite? Little l2, they are square summable sequences. So you see how square summable sequences are going to play a very fundamental role in everything. We start by saying our system is going to be described by a state vector in some separable Hilbert space equipped with some orthonormal basis, and then since I am going to look at these vectors are going to have physical meaning, and these are going to be, we are going to insist they have finite norm. So this quantity should be less than infinity. Then our knowledge of this state vector can actually be summarized by our knowledge of these coefficients here in this basis, and these coefficients would belong to little l2. So that is how little l2 is going to play a very basic role in everything. Okay. Of course we also know how to go from one basis to another. Basis sets are not unique. We saw that the formula for translating from one to the other is very straightforward. All you have to do is to use the completeness of these basis vectors, insert the identity operation at all times. So in other words, phi n phi m equal to delta nm and summation over n phi n equal to the identity operator. This is orthonormality and this is completeness. And to go from one basis to another, etc., it becomes very trivial as long as you go on inserting the identity operator in between. Okay. Now coming to operators, operators act on vectors in a linear space, and linear operators are those which act in a linear manner. In other words, A is a linear operator if A acting on psi plus chi equal to A acting on psi plus A acting on chi. This is the first thing you need, and A acting on A times psi, let us call this some C times psi, where C is some scalar which multiplies this vector of a linear vector space. This is the same thing as C A psi. Okay. Moreover, A plus B acting on psi is the same as A on psi plus B on psi. If A and B are linear operators, then this is also true. Okay. And A acting on B psi is the same thing as AB acting on psi. By definition, this is the way I define what is meant by the product of two operators, just successive operation. Not the same as BA times psi, of course, because operators do not commute with each other in general, and that is the whole point. Okay. Now let us put in a little bit of physics into this business, and I am going to do this by defining a whole set of postulates, and these postulates have come based on our experience with quantum mechanics, ultimately based on experiment, tested with experiment, but at the moment we can write down a fairly axiomatic formulation of quantum mechanics. Okay. And then of course the test is finally to ask if its predictions of this theory or this way of calculating are compatible with experiment or not, and to the best of our knowledge over the last 100 years quantum mechanics has stood the test of time, it has not failed. There are still many unresolved questions in it, there are very delicate questions of interpretation which have not been taken care of fully, but as a calculational tool, as a formalism, it is in fact quite pakka, quite robust, and has been tested over and over again, and as far as we know there are no violations at all. So let me start not necessarily in the best order, but in some order. Okay. So whenever I make a postulate, let me put a little dot here to show this is an axiom, one of the axioms. So I start with a very general thing, and then of course we will make it very much more specific. Every system, every dynamical system, by this I mean dynamical systems, physical systems of some kind, we will not specify too accurately right now, we will make it more specific as we go along. Every system is described by a state vector, it is called a state vector. In the same breath let me also say, we will see a little later that this is not the most general way of describing systems in quantum mechanics, but for the moment we start with this. Every system is described by a state vector psi, say, just for notation let me call it psi, that is an element of a Hilbert space. Of course different systems would have different Hilbert spaces. Now what do I mean by a system? It could be one particle, 10 particles, a collection of particles, this object, a human being, all the people in this room, this earth, this galaxy, all these are examples of physical systems, and the statement is, modulo some qualifications, that every one of these systems is described by its own state vector, and the presumption is that all the information you can get about the system is buried in this state vector, everything is in this state vector, and the question is, the next subsequent rules of quantum mechanics tell you how to extract physical information given the state vector from the state vector. This state vector, since it is a dynamical system we are talking about, this state vector psi is a function of time. Right now we are talking about non-relativistic quantum mechanics, so I am assuming what you would assume in Newtonian mechanics, namely a working, there is some frame of reference, there is an observer in the frame of reference, etc., and time is the variable in which dynamics occurs, and the state vector is a function of time. And the next thing of course would be to say it changes with time, as the state evolves, as the system evolves, it changes with time, and the rule we need is to say how does it change with time. The analog of what you would say in Lagrangian or Hamiltonian mechanics, where you would give rules or equations saying how the q's and p's of a system change with time. This is what we will do next, but we need a few more preliminaries. Every system is described by a state vector. Then the question is, what are physical observables in the system? What are the physical properties of the system? For this purpose it is convenient to think of this system as a particle, it is very convenient, that is the way you do mechanics too, by starting with one particle and then you assign coordinates and momenta to it, or coordinates and velocities. In the same way I think of a particle and it is in interaction with the rest of the universe and I assign a state vector to it. Then it has physical attributes, this particle has a momentum, it has velocity, it has position, it has other physical properties such as angular momentum or energy and so on. Now what are these things, what do these correspond to? In quantum mechanics, physical observables, dynamical variables or physical observables also called measurables, physical observables are associated with operators. So for every physical observable there is an operator, for the position there is an operator, for the velocity there is an operator, for the momentum there is an operator, and so on. For every physical observable you can associate with a system there is an operator, not necessarily independent, because if you look at the kinetic energy which is half mv squared for a particle, of course once you give me the velocity operator I know the kinetic energy operator, but with every observable I associate an operator. Then the question is, what values can these operators have? After all, given an operator you have to associate some value with a physical observable. How do you associate a value with an operator? The natural way to do this is to talk about the eigenvalues of this operator, because the eigenvalues of an operator are those quantities. So given a linear operator A, so this is going to be our basic equation. If A is an operator in a linear vector space acting on a state vector psi, and this is equal to lambda times psi for some special value of lambda and special value of psi, special vector psi, that is an eigenvalue equation, then lambda is an eigenvalue of A with eigenvector psi. Okay. Of course a given operator in an abstract sense may have lots of eigenvalues. Think of a matrix, think of a finite dimensional vector space, then psi could be written as a column vector in n rows and one column. Then every operator A can be written as an n by n matrix. and when it acts on this column vector it produces another column vector in general, but there are special values, there are special column vectors such that when this matrix acts on those column vectors it reproduces the same vector multiplied at best by a number, by a scalar, and those scalars are called the eigenvalues, and these are the eigenvectors, exactly as you have in matrices. Now of course for a given eigenvalue lambda you may have more than one eigenvector, then you would say this eigenvalue is a repeated eigenvalue. If there is more than one eigenvector, if you have two or more linearly independent eigenvectors corresponding to a given eigenvalue, then the eigenvalue is a repeated eigenvalue or a degenerate eigenvalue, that is possible. It is also possible that the number of eigenvalues is infinite if the vector space is infinite dimensional. If it is an n by n matrix, then of course you can at best have n eigenvalues which could or maybe distinct complex numbers or maybe degenerate partially, but in an infinite dimensional space you may have an infinite number of eigenvalues. So that not going to bother us at the moment. So this is an eigenvalue equation, and the statement we need, the postulate we need is to make sure that the eigenvalues, which in some sense will be the only measurable values of an operator corresponding to a physical observable, should be real. If the observable you are talking about is a real observable, physical observable, then the eigenvalues should be real, and there is a theorem which guarantees the kind of operators which have real eigenvalues, and those operators are self-adjoint operators. What kind of matrices have real eigenvalues? Square matrices. Let us talk about n by n matrices. So an arbitrary n by n matrix in general has complex eigenvalues, n complex eigenvalues. When are you guaranteed that the matrices have only real eigenvalues? If it is real symmetric, yes, if the entries are real and the matrix is symmetric, you are guaranteed that the eigenvalues are real, but if the entries are complex then symmetry is not enough. Hermitian conjugate, if a matrix is Hermitian, in other words if it is equal to its Hermitian conjugate, then the eigenvalues are real. So then all the eigenvalues are all real, all the eigenvalues are real. Now of course for matrices it is quite clear, if you give me a matrix I can inspect and find out if it is Hermitian or not. If it is Hermitian the eigenvalues are guaranteed to be real, if not that is not true. But for arbitrary operators, maybe differential operators, integral operators and other complicated operators, you need a generalization of the idea of a Hermitian conjugate, and I am going to call them self-adjoint. And I gave an example of this with the derivative operator. You notice on an L2 space, function space, capital L2 space, I defined the operator d over dx, the derivative operator, and then I said let us look at those vectors which remain in the space when d over dx acts on it, and then it turned out that the adjoint of d over dx was minus d over dx. So that operator is not self-adjoint, and there is no guarantee the eigenvalues are real. Now that is immediately obvious, because if I put e to the power ix and I do d over dx, I get I e to the power ix. So there is an eigenvalue which is I. On the other hand, you are guaranteed, absolutely guaranteed, that if the operator is self-adjoint then the eigenvalues are real. So physical observables are associated with self-adjoint operators. That is put in. A little later when we look at problems involving one dimensional motion and so on, then I will point out carefully the difference between a Hermitian operator and a self-adjoint operator. Actually there is a subtle difference, and it is not necessary that a Hermitian operator be a self-adjoint operator, although in elementary treatments on quantum mechanics these two words are used interchangeably, because in the case of matrices they mean exactly the same thing, but we got to be a little more careful. At the moment let me be rigorous and correct and say that the operators have to be self-adjoint operators. By the way, this would imply all eigenvalues are real. Now of course you have to allow for another possibility right away. The number of eigenvalues of an operator may be infinite. It is also possible that the eigenvalues are not even countable. For instance, if I look at the position of a particle moving on a line, continuous line minus infinity to infinity, this position can take on an infinite number of values, a continuous infinite number of values. Therefore we must allow for the fact that the set of eigenvalues of an operator may actually be a continuous set. The eigenvalues are not even countable, and that is a very important possibility, and we need to take care of it. So right away it says that matrices may not be enough to do this whole thing, because there would be more general operators which would have continuous sets of eigenvalues. On the other hand, I look at the matrix, I know its eigenvalues are all countable, even if infinite number in number it is still countable. So we must allow for this possibility. So for the moment therefore I simply say all the eigenvalues are real, the operators are physical quantities are associated with self-adjoint operators. Okay. These operators will act on the state vector, possibly produce other state vectors and so on. Okay. Then the result of the measurement of any physical observable is always an eigenvalue of the corresponding operator. So you make a measurement on a system described by some state vector. The measurement has to be designed by you cleverly to measure some physical quantity, and the result that you record will be a real number, and it is guaranteed to be one of the eigenvalues of the operator associated with this observable. What is not clear and what is not definite about quantum mechanics is that you cannot a priori say which eigenvalue is going to emerge. This is where quantum uncertainty comes in. It will be one of the eigenvalues, but you can't say which one before the measurement. On the other hand, you can repeatedly make lots of measurements, take the average, it would be some weighted average over all the eigenvalues, and you would call that the mean value of this observable. So you can do this by preparing a system, identical copies of a system, imaginary copies, making a measurement on copy 1, copy 2, copy 3, etc. all the way, take the arithmetic average of the results, and that would be, this is a distribution, an ensemble, and the result would be the mean value or the expectation value of this operator. And what quantum mechanics does is to give you a rule for calculating the expectation value. So let me repeat this again, because it is a very basic point. It is imagined that every system is described by a state vector. I would like to take this system and measure, let us say, its angular momentum. In classical physics, once I identify the generalized coordinates, generalized momenta and so on, I have a formula for the angular momentum in terms of the q's and p's, and in principle there is nothing to stop me, given initial conditions, finding what these q's and p's are at a later instant of time, and I can calculate its angular momentum. You can then measure it, test it against experiment. In quantum mechanics, if the system is a quantum system, then if it is in some state, we do not know what state, we assume that we know the state of the thing, but it could be in any state whatsoever given some state. I measure by an apparatus designed to measure angular momentum, I measure the angular momentum. The answer I get is going to depend on the state in which the system is, but the answer I get even for a given state of the system in general cannot be predicted before the measurement. Even with the knowledge of that state, you cannot predict the answer. What you can do, however, is to be sure, what you are sure of however is that when you make this measurement the result that comes out will be one of the eigenvalues of the angular momentum operator. Which eigenvalue it will be you can't say before the measurement. Okay. So what does one do? One imagines making an infinite number of copies of the system all in the same state, and then you perform measurements, or different people perform measurements on different copies of the system, and then you record all the answers. In the first measurement maybe eigenvalue lambda 1 emerged, in the second measurement eigenvalue lambda 6 emerged, and so on. You add up all these guys and take the arithmetic average in the limit in which the number of measurements is infinite number of copies. That would be the average value of this observable, this physical observable, and it is called the expectation value. And quantum mechanics is going to give you a rule for calculating the expectation value. This is what it will do, and that is going to be our target. What is the rule for calculating the expectation value? Of course it will also give you a rule for calculating the scatter about the expectation value. It is no good just giving you one number, it is like giving you an average, it will give you the mean square, the mean cube. So it gives you rules for calculating every one of the moments. Now you can conceive, it is conceivable of course, you can immediately imagine that if I make a sufficient number of measurements on my physical system and compute a sufficient number of moments of each of these observables, then in principle I know everything I need to know about the system. All information I want about the system is acquirable. So that would be our target, to find out what kind of measurement should be made on a system in order to find out everything about the system, all possible physical information, and there are some twists on the way in doing this. Now this is the probabilistic content of quantum mechanics, namely it gives you a rule for calculating average values, mean square, mean cube, and so on. So in that sense it is a probabilistic theory in that particular sense. So is this clear? This is, yes.
So does it mean that quantum mechanics does not provide with time evolution equation?
No, since we are going to come to that. The rule that I am going to talk about is going to depend on the state vector. The rule will involve the state. It says in this state this is the expectation value. Now of course if the state changes from one instant of time to another, you need to know what the rule is by which this state vector changes. That rule will be provided, that will be one of the postulates, and that rule is called the Schrodinger equation. That is precisely the Schrodinger equation. The Schrodinger equation is just the differential equation that tells you how the state vector of a system evolves in time. Therefore you can calculate the state vector at any instant of time given the initial state vector, that is definite. But even a knowledge of the state vector is not enough to give you 100% reliable prediction on what the result of a measurement is going to be. Okay. That is the way quantum physics is. Yeah.
What fundamental factor of the quantum mechanics
yeah.
which gives that shift, that is from deterministic than probabilistic method? Suppose we know the state of the system a priori.
Yes.
Classical mechanics, knowing the state of the system, we can find the say angular.
Absolutely. Yes. Yes.
Eigenvalue.
Yes.
But from your explanation it turns out that in
Yeah.
quantum mechanics we will get different eigenvalues.
Yes, absolutely. Very good point. The point is it possible that the state of the system is such that I can gain complete information about the system? Go back to classical mechanics, look at a single particle moving in one dimension. It is described by generalized coordinate q, a coordinate q and a momentum p, and therefore in phase space in the qp plane I specify a point. That point tells me everything I need to know about the system, that is it. Those are the only attributes, independent attributes of the system, and I know it completely. In quantum mechanics I am saying that the system is described by a state. Now suppose you take the same system, same particle, it is quantum mechanical, and let us say that the independent dynamical variables are its position and its momentum in one dimension. Then the question is there a state of the system such that the position has a sharp value? So I give you the state and I immediately know the position. In other words, is it a position eigenstate? If it is, then of course I apply that position operator on the state vector, I get a number and that is it, there is no distribution. The answer is yes, you have position eigenstates. Then the question is, are there momentum eigenstates? The answer is yes, there are momentum eigenstates, but no state can be simultaneously a position eigenstate and a momentum eigenstate. Such a state does not exist. So that is where the uncertainty comes in. So it will turn out that for those variables which are canonically conjugate in the classical sense, namely the Poisson brackets are equal to 1, for those variables in quantum mechanics it is impossible to find simultaneous eigenstates, and therefore both x and p cannot, there can be no state of a system of the particle in which both x and p can be simultaneously specified to infinite precision.
Sir, to have a mean you need all the eigenvalues.
Pardon me?
To have a mean.
Yes, I need all the eigenvalues. I need.
You predict even after an infinite experiment, all the eigenvalues will emerge. It may happen so one emerges twice, thrice like that. How can I guarantee that all will emerge?
Yeah, the question is it possible that I may miss out on some of the eigenvalues when I make measurements? The point is, if the system has given the states of the system, the idea is that the states will cover all possible values of all possible observables, only then would it be a complete Hilbert space. So everything is included, all possible eigenvalues, may be highly improbable and so on, may take special efforts, you may need special efforts to produce a state of the system corresponding to a very large eigenvalue of some observable, but the idea is they are also in the same space, nothing is left out. Yeah.
So you mentioned about the eigen position.
Yes.
Sir, that gives us the position of the system instantly.
Yes.
That means without doing the experiment we are getting the value of the position.
No, it is not a question of without doing the experiment. The point is that you want to describe the results. What is the whole idea of physics? You want to describe the results of experiment, so you need a formalism which will tell you how to calculate, and then you compare with the experiment. So these are two different things. The system is a part of nature, it is acting in some fashion. Quantum mechanics is a formalism which helps you to describe this system in precise terms. So I would always like to have rules of computation, of calculation for physical quantities which I can compare against the results of measurements. Okay. So we will not confuse the formalism with the actual experimental observation or the measurement. These are two different things altogether. Right. I always need something to calculate. Yeah.
So you mentioned that we can't predict the state without doing.
Yes. No, I didn't.
It can be any of the eigenvalues.
No, the statement I made was, given an arbitrary state of a system, and all these things will become clearer as I give examples, given an arbitrary state of a system, if I look at some particular physical observable corresponding to the system, such as the position of a particle, then in an arbitrary state of the system, if I measure the position of the particle, the answer I get is guaranteed to be one of the eigenvalues of the position operator, but I cannot tell you a priori which eigenvalue will emerge on the basis of one measurement, even if I know the state of the system. What I can do is to assign probabilities with which different values, eigenvalues would emerge given that state of the system. So suppose the position, for just for example, let us say you take some physical observable corresponding to a system, and let us say this observable can take the values 1, 2 and 3, those are the only eigenvalues allowed no matter what state you are in. Okay. Now I put the system in an arbitrary state, I make a measurement, I may get the value 2, I make another measurement on an identically prepared copy, I may get the value 3 and so on. Given the state of the system, I can't tell you whether I am going to get 1 or 2 or 3 in a given measurement, but even before you make the measurement I can tell you the probability with which you are going to get eigenvalue 1 is P1, and similarly for P2 and P3, that I can tell you based on a knowledge of the state of the system. Therefore it follows that 1 times P1 plus 2 times P2 plus 3 times P3 is after all the average value of this variable. If I took an infinite number of copies of the system identically prepared and made measurements, I would get 1 a large number of times, 2 a large number of times, 3 a large number of times. I draw histograms, how many times do I get 1, 2, 3 and so on. Then the relative fraction of times I get P1 is of course P1 and similarly P2 and P3, right. Now what I can tell you from a knowledge of the state of the system is I can give you the numbers P1, P2 and P3, right. And of course once I give you P1, P2, P3, you will say 1 times P1 plus 2 times P2 plus 3 times P3 is in fact the average value, and that is precisely what you will get by making this infinite number of measurements and taking the arithmetic mean. Okay. So that is the sense in which quantum mechanics is probabilistic. Yeah.
So, will the average value be one of the eigenvalues?
Could be, but the average value of the height of the students in this room need not be one of the heights of the students, need not be. The average value of a set of integers need not be an integer. It could be, depends on the distribution. Yeah.
Sir, is this a shortcoming of quantum mechanics or is nature inherently random?
This is what the very deep question. His question is this a shortcoming of quantum mechanics or is nature inherently random? Our belief is that nature is this way. Our belief is that it is not an artifact of, first it is not a failure of experiment. So the uncertainty in quantum mechanics is not due to the fact that you do not have sufficiently precise measuring instruments. Even if you had infinitely precise measuring instruments, this would still be the case. Second, it is not, we believe, not an artifact of our formalism of quantum mechanics. We believe it is because there exists a fundamental constant called Planck's constant which is non-zero. So the fact its numerical value is irrelevant, that is 10 to the minus 34. Its numerical value is linked with the fact that objects as big as us do not have many quantum corrections. I mean, we know we are essentially classical. Objects like electrons, the quantum corrections would be very significant. That is what the numerical value of Planck's constant determines. Had Planck's constant been 34 orders of magnitude greater, then of course quantum uncertainties would be so wild that we would not have the classical world we have. But the fact that it is non-zero is what is leading to quantum mechanics, and we think that that is what it is. This is what it is. Why, we do not know. The why of it we do not know. I do not know if we can ever know the why of things at an ultimate level always, because this ignorance will simply be pushed back one step further to whatever, if in future some other theory subsumes quantum mechanics and is a superior theory which actually includes quantum mechanics as a special case, even then the question would persist, why that? Okay. Yeah.
So you said that make copies of system.
Yeah.
What do you actually mean by saying copies?
Well, suppose I asked you to measure the resistance of 1 meter of copper wire. The two ways in which you do this, you take a long spool of copper wire, a kilometer long, cut it into 1,000 meter lengths and have 1,000 different people make measurements, one each. That would be an ensemble average, right. The assumption is that the copper wire is homogeneous and therefore whatever is 1 meter here is the same as 1 meter there and properties have not changed and so on and so forth, and that gives you the arithmetic average, right. So that is the sense in which I say make copies of the system, and in principle you need an infinite number before you get the true arithmetic average. Of course in dynamics, remember that we talked about ergodic systems, there we said that the time average is equal to the ensemble average. So the idea was you do not have 1,000 pieces of copper wire, you have just one piece and you make it repeatedly, you go on making measurements on this one piece, and the presumption is that all the values or realizations that these 1,000 pieces of wire would have given of this random process of this random variable would already be realized as time goes on in this single piece of wire, and that is what we call ergodicity, where I said the ensemble average is equal to the time average here. Need not always be true, of course. So that is a specific assumption in dynamical systems. We are not making any such assumption here at the moment. Yeah.
Do these eigenvalues span the entire real line, or
we do not know. We do not know, we have no idea, it depends on the system. Now there are cases, all we have said is physical observables, which are real observables, should really have real values when you make measurements, and therefore we look for all those operators which have real eigenvalues, and they are self-adjoint operators. Now the spectrum of an operator is a set of its eigenvalues, is called the spectrum of an operator. may be continuous, may be discrete, just real numbers, could be integer valued, could be non-integer valued, could be continuous, could be partially discrete, partially continuous, and so on. Let me give you an example. The energy of an electron in a hydrogen atom in quantum mechanics, as you know, is minus 1 over n squared in Rydberg units for the bound states, but then those are negative energy states and they are all discrete, minus 1 over n squared where n runs 1, 2, 3, 4. As n becomes larger, these states come closer to 0, and then all possible positive values are also allowed. So that spectrum consists of this set, it consists of minus 1, minus 1/4, minus 1 over 9, minus 1 over 16, 0, and then all positive numbers. That is the total spectrum of an electron interacting with the proton by Coulomb interaction in quantum mechanics. So the negative numbers are the bound states of the hydrogen atom, and the positive numbers correspond to a free electron scattering off a proton. They are all part of the spectrum still, and what will become significant is that the state of the electron, the state of this system in this part of the spectrum is very different from the state of the system there, and that is what will distinguish the scattering states from the bound states.
Sir, is it possible to make a measurement without changing the state of the system?
Now this is again a very deep question. Does it change the state of the system when you make a measurement? This is a very deep question, and this is where the problem of measurement in quantum mechanics arises, and that is where there are grey areas still. The answer of course is, in general when you make a measurement, if you produce an eigenvalue as the answer, it implies that the measurement has somehow converted your state into an eigenstate. If I make a measurement on this and I get lambda 1 as the eigenvalue and psi 1 is the eigenvector corresponding to the eigenvalue lambda 1, it implies that this operation of measurement has somehow affected the system and instantaneously changed its state from whatever it was to the eigenvector psi 1. So definitely it has made a change. On the other hand, if the system was already in the eigenstate psi 1, I make a measurement, it remains where it is. So measurement in general changes the state of the system quite drastically, and it is called the collapse of the wave function in quantum mechanics, and one interpretation of quantum mechanics assumes that by some mysterious as yet unknown process, any measurement of a physical observable on a system collapses the state of the system instantaneously to one of the eigenstates, after which the Schrodinger equation will take over and the system will evolve once again, etc. So the idea is that if you make an instantaneous measurement immediately after you made a measurement and got the eigenvalue lambda 1, you will still see lambda 1. How long it will take to decohere and become something else is dependent on the Hamiltonian of the system. Okay. On the other hand, there are interpretations of quantum mechanics which do not talk about instantaneous collapse at all, but use totally different premises to explain the measurement process. Okay. So the measurement process, the process itself, the details of the measurement process itself is something we will push under the carpet. We will not talk about it here because that is the part of quantum mechanics which is tricky and is open to interpretation. Okay. This room is adequately carpeted, so I can push all these things under the rug, but you are completely right that in general the measurement changes the state of a system, but it need not under special cases. Yeah.
Then do all states of the system have to be eigenstates?
No, absolutely not. So we are coming to that. Do all states of the system have to be eigenstates or not? Let me give you a specific example of what will happen, and this is in fact going to tell us how to calculate expectation values, and it will also lead us to the probabilistic interpretation of quantum mechanics. We could have started with that the way for example it is done in the Feynman lectures and then work back to expectation values, but I would like to start from here and go back because I am going to assume that it is easier to understand classical probability theory, and then I point out where quantum probability differs from classical probability. The whole thing can be looked at in yet another way, which is a small change in the rules of probability theory, and that takes you from classical to quantum mechanics. So suppose you have a physical observable associated with which is the operator A, and the state of your system. For the moment let me assume everything is being done at one particular instant of time, so I will not put in the time variable. So let us suppose this is the operator and the state is psi. Then the question is, what is the average value that I am talking about, which you get when you measure A repeatedly in over an ensemble or collection. I call that the expectation value. I am going to denote it by this number, 2 angular brackets to denote the expectation value. And as I mentioned, quantum mechanics gives you a formula for this quantity here. Now how are we going to interpret it? How are we going to calculate this quantity? And buried here in this formula is in fact the probabilistic interpretation of quantum mechanics. One starts by saying, let, for convenience, let us assume that this physical quantity corresponding to the operator A has a set of eigenvalues, lambda 1, lambda 2, etc. For the moment let me assume the eigenvalues are countable, so I will write them as lambda 1, lambda 2, etc. So let lambda 1, lambda 2 be the eigenvalues of A with eigenvectors phi 1, phi 2 and so on. Okay. And for ease of notation let me assume these are all non-degenerate, they are all real numbers because A is a physical observable, so the eigen operator is self-adjoint. And let me go a step further and anticipate myself and say that these phi's can be made into an orthonormal basis set. Now the immediate question is, given a physical observable, can you always make an orthonormal basis set out of its observables? For ease of presentation let me assume I can for the moment, we will see what happens when you can't later on. So this this set here forms a basis set. Now what does that imply? That immediately implies that psi can be written as summation n equal to 1 to infinity some coefficient say Cn phi n. So this is a set orthonormal basis. I am going to assume that they form an orthonormal basis, then I can write this psi in the form Cn phi n. Pardon me? Psi is the state of the system. This is my state of the given system. Then what is the Cn? The Cn we know is equal to phi n psi. What is the interpretation of the Cn? That is the question, key question. It is just a coefficient in the expansion of a vector. So it sort of tells you how much of the vector psi is pointing along the vector phi n. That is all it is, right? I mean, if symbolically if this is psi and this is for example phi 1, then this quantity here is nothing but the projection of the psi into this direction here. So if you like, it is this vector. If I multiply this by phi 1 on the right hand side, it will in fact give me the component of this vector along this. That is mathematics, it just tells you you projected this and it is only the coefficient tells you how much of it is along that. Now the interpretation in quantum mechanics comes by saying this quantity is the probability amplitude that when the system is in the state psi it is actually the state is phi n. So it is the probability amplitude, not probability, probability amplitude, and that is a term that is introduced, it is a non-classical term, it is a specifically quantum mechanical term that is introduced to say that it is the probability amplitude that the state is actually phi n. Of course you would say what is the use of the probability amplitude, I do not know what the probability is. The next postulate in quantum mechanics says the mod squared of this quantity is the probability, and that is the postulate. But this itself is a complex number, but you are guaranteed for any complex number the mod squared is always a non-negative real number, and therefore that is associated with the probability. So this is one more way of introducing quantum mechanics. You could start by saying that these quantities, these inner products are probability amplitudes such that it is the probability amplitude that this event is in fact this event, or this state is in fact this state. And it will work even with time, as you can see. So if I have a state at some instant of time and I have another state at another instant of time, this inner product, the initial state here and the final state here, is the probability amplitude that this guy has an overlap with that, and that will tell us how to compute these numbers. So let me do this next time, which is tomorrow. We will start at this point and I will show you how this definition of this quantity as a probability amplitude immediately tells you what the probability distribution itself is. Okay. Then we look at specific examples. Okay. Yeah.
You mean that you make a measurement, you get phi n with probability Cn squared.
Yes, mod Cn squared. Yes.
Mod Cn must be less than.
We will come to that. Now it is clear, it is immediately clear from here that if this, if psi equal to 1, then n, if this is true then that is equal to this, we already saw this. So this is a sum of non-negative numbers, so each mod Cn squared must be less than 1 and therefore is a probability. That is the whole point.
Sir, is the state of the system defined by all its physical observables as a instant?
Yeah, so the whole idea of quantum mechanics is the state of the system is some abstract guy, some abstract object, and everything about the system is buried in there, it is encoded in there.
Why isn't the state subject to as much uncertainty as its components?
The state of a system, there is nothing, that is the way nature is. The state of the system is not an observable by itself, it is something from which you derive expectation values of observables, but it is not an observable itself. It is a false analogy, but it gives you a good picture to say the state of the system plays the role of something like the probability distribution of a random variable. The probability distribution is not an observable of a random variable, is not an observable, only the average, the mean, mean square, etc. are observables, but the distribution helps you compute these quantities. And quantum, anything you can see, anything you can measure. Yeah, I will write this down clearly and then you will see what the Cn is. It is the probability amplitude that indeed, or better still I should call it an overlap between the state psi and the state phi n, which is what the geometrical interpretation is. But the postulate of quantum mechanics is the mod Cn squared is the probability that the system when it is in the state psi is in the eigenstate phi n. That is the exact statement. Yeah. Pardon me?
Why mod Cn squared?
That is the only quantity which has the desired properties. They are real numbers, they are between 0 and 1, they are normalized to unity. Why not mod Cn itself? That is the way quantum mechanics is. That is the way it is. It is not mod Cn, it is not mod Cn to the power 1/3, no, it is mod Cn squared. That is the way it is. Okay, that is the consistent way, only consistent way we can write down quantum mechanics. Okay. Yeah, because of the inner product equation, but yeah, surely, but you know the point is you could have started with a different formalism altogether. That is not the way it operates, this is the way it is. Okay.